Hello, so this is my proof presentation for proof 2.2, and it is all about moment generating functions. So we have some random variable x, and the moment generating function, call it mgf, of x is defined to be the expected value of e to the tx. So our first task is to prove that the nth derivative of, and we'll call this m of t. So our first task is to prove that the nth derivative of our moment generating function evaluated at t equals 0 is in fact the nth moment of our random variable x. So we want to show that the nth derivative evaluated at 0 is equal to the nth moment of x. So that is our goal. So, well, we can start by expanding this out into its Taylor series expansion. So the expectation of e to the tx, so just recall that e to the tx, we can expand that out as 1 plus tx plus t squared x squared over 2 factorial plus dot dot dot. So I'll write out one more term here before I just write dot dot dot. And now we remember that that our expectation operator is in fact a linear operator, so we use linearity to say, well, the expectation of 1 is just 1, right? And then we get plus t expectation of expected value of x plus t squared over 2 times, well, what's that, the second moment of x plus dot dot dot. Right, so that is just another way to write our moment generating function. Well, let's see what happens when we start to take derivatives of our moment generating function. So it turns out that we can take the derivative of this function just by taking the derivative of each term. We won't go into why that is, but that works out with power series. So first derivative of our moment generating function is, well, that 1 disappears, and we just, that t disappears, and we get first moment of x times, well, then 2 times 1/2 is 1, so t expected value of x squared, and the next term would be t squared over 2 prime, or 2 factorial times third moment plus dot dot dot. Now, let's try to see if we can see any pattern coming up here. Take second derivative. Well, this expected value is just a real number, so that would just disappear just like our 1 disappeared above it, and derivative of this term is just, in fact, the second moment. And then we take the derivative of this, we see that that's just t times the third moment. Plus dot dot dot. And I think that we're starting to see a pattern here. So if we kept on taking, so if we took the nth derivative of our moment generating function, we see that that would just be, that would just be the nth moment plus t plus t expected value of the next moment plus t over 2 factorial expected value of the n plus second moment plus dot dot dot. And now we see that evaluating this nth derivative of the moment generating function at 0, that that each term, a factor of t can be taken out of each term except for this very first one. So evaluating at t will make everything else 0 except for this first term. So the nth derivative of our moment generating function evaluated at 0 is just the nth moment, as we wanted to show. And this works as long as your random variable actually has a moment generating function. So the second part of this proof I'll label this 2 just to show we're moving on to something else now. So we say we have 2 independent variables, so x1 and x2, just this little orthogonal sign as a shorthand that they're independent, and they have respective moment generating functions m1 of t and m2 of t. So m1 of t is the moment generating function for this guy, m2 of t is the moment generating function for this guy. And we want to show that the moment generating function of the random variable this guy plus this guy, because if you add two random variables you get a random variable, this guy's moment generating function is in fact the product of the individual moment generating functions. So that's what we need to show. Well, let's start from the definition of this guy. That is the expected value of e to the t times the random variable, which is x1 plus x2. And we can just rewrite that as the expected value of e t x1 e to the t x2 and here's where the fact that these two random variables are independent comes in. So independence implies uncorrelated, and uncorrelated tells us that we can write this as the product of the expectation of this guy and the expectation of this guy. And well, what do we have here? We note that just by definition of the moment generating function of x1, this is the moment generating function of x1. And likewise, this is the moment generating function of x2. So, just to write out what we've demonstrated that the moment generating function, that if x1, I'll write it out like that, so x1 and x2 being independent implies that, should they have moment generating functions, that the moment generating function of x1 plus x2 is equal to the product of each moment generating function, respectively. And as it turns out, this is really an if and only if statement, but we are not proving it in the other direction. So we are done with this proof.